Okay, we will try to do this question. This is related with phase modulation. So we have derived the narrowband phase modulated signal. Okay, so you can go through that tutorial session and find how the derivation is done. I think you can remember that we have used that identity cos alpha plus beta is equal to cos alpha cos beta minus sin alpha sin beta. And in narrowband assumption, we have assumed that cos phi t is nearly equal to 1 and sin phi t is nearly equal to phi t. Okay, so using this identity, we can write this as xct equal AC cos omega ct plus cos omega ct cos phi t. So you can see that this is a function of a function minus AC sin omega ct sin phi t. Okay, so this is equal to phi t and this is equal to 1. Okay, so you have the expression for the narrowband phase modulated signal. So it is XPF phase modulated narrowband. X narrowband phase modulated signal is equal to AC, this part is 1. Okay, so use this assumption. So AC cos omega ct minus, so this is phi t. So we have AC phi t sin omega ct. So this is the narrowband assumption. So why we use the narrowband assumption actually? So here you can see that here we have a function of a function. So when we are dealing with the frequency domain, it is hard to find the frequency domain signal of this kind of function. So we eliminate this function of a function term using the narrowband assumption. So now we have one function and product of two functions. Okay. So that is the advantage of this narrowband assumption. So we have already derived the spectrum for narrowband assumption. So I'm not going to derive it here. Please go through that tutorial session. It is frequency domain analysis of phase modulated signal. That is the tutorial session. So you can go through that. Okay. So here narrowband PM, if become as I can remember. So you can see that here we have to get the Fourier transform of this function. Okay, so it will be half AC delta F minus FC plus half AC delta F plus FC. So this is the Fourier transform of this cos omega t. Okay, and we have to get the Fourier transform of this function also. So you can see that we have done the modulation theorem. We have derived the modulation theorem. So you can use the modulation theorem to derive this. Okay, to get the Fourier transform of this term. Okay, so we can directly write it, no? So please go through that modulation theorem tutorial also, that in that question also. So you can understand how we can get it. So using the modulation theorem, we can write this term as, okay, we can write this term, okay, this term as, so J terms is come here, J AC by 2. So I think here it is come 5 F FC plus J AC by 2 5 F plus FC. So this is the Fourier transform of this one. Okay, please go through that modulation theorem session and frequency analysis of phase modulation session and find the frequency domain representation, frequency domain signal. Okay, so normally this is minus side parts, no? This one and this one, minus side part. So if we do the frequency domain signal, so here F delta is shifted to this way by FC. Okay, so we have one impulse here, and here it is shifted to, for this term, it is shifted to here, no? FC minus FC. Okay, so for this part you will have this kind of spectrum. Okay, and for this part you will have this kind of spectrum. So normally we draw only this spectrum, plus side spectrum, we doesn't draw this spectrum. So normally we use only these two terms, no? We eliminate these two terms. We normally don't use these terms. Okay, these terms. We only use this plus side spectrum parts. Okay, so this is the narrowband frequency spectrum. Okay, so if we go to the next question, okay, so here you can see that we have given the message signal, no? This is message signal. So if we, so we have to find the power spectrum. Okay, so we know that the power spectrum, okay, power spectrum, we will use only plus terms. Okay, that is half AC delta F minus FC plus half AC 5 F minus FC. Okay, so and also you can remember that the minus term is also there. Okay, minus term is also there, that is FC plus FM, and here also FC plus FM term is there, but we have eliminated them. We only consider this plus side band. Okay, for example, you can write, for example, you can write only these terms, these two terms. Okay, so so you know that here we know that 5t is equal to 5 delta xt. Okay, so I think you can remember that this is phase deviation. Okay, so there is upper bound for phase deviation, that is 180 or 5 radians. Okay, this is the upper bound for phase deviation. Okay, so so I think you can remember that this phase deviation is equal to Kp, phase sensitivity. This is phase sensitivity. Okay, sensitivity into AM. Okay, so AM is modulation, modulating signal, message signal, amplitude. Okay, so if you consider this phase deviation, the amplitude of the message signal is already there. Okay, so we have to get the nominalized message signal, this one. That means our real message signal should be divided from its maximum amplitude. Okay, so we will get the nominalized message signal. Okay, so I think you can remember these things. We have discussed several times those. Okay, so so you can see that if I consider 5t, okay, so here 5t is equal to 5 delta, and what is xt? Our message signal, that is sync square omega t. No, that is sync square omega t. Okay, so this is our message signal. Okay, message signal, nominalized message signal. Okay, so so to find the Fourier spectrum for this signal, what we have to do? We have to calculate only these terms, no? Only we have to calculate only this term. Okay, so how to calculate this term? Okay, so you can see that if we can calculate the 5f, okay, that is the Fourier transform of this 5t. Okay, so if we can find the Fourier transform of this 5t, 5f, then we can find this term easily, no? Okay, so we will try to find the Fourier transform of this 5t. Okay, this signal. Okay, so this is our message signal. Okay, message signal into phase deviation. Okay, so so to find the Fourier transform of this 5t, okay, we have to find the Fourier transform of this 5 delta sync square omega t. So this is constant. 5 delta phase deviation is a constant, it is a number. Okay, so I can get out of this 5 delta. Okay, so only I have sync, sorry, this is sync square omega t. Okay, so we have to find the Fourier transform of this sync square term, no? So actually we couldn't do that one, no? We couldn't do that one. We only find the Fourier transform of this, of a sync pulsion for a sync function, not a sync square function. Okay, so sync square function is like this. You can remember, no? It is like this. Actually, it is not like this. It is like this. No, it is like this. Okay, so this is 0. Okay, here it is 5 by omega. Here it is 2 5 by omega. Here it is minus 5 by omega. Here it is minus 2 5 by omega. So on, no? Okay. So what is the Fourier transform of this function? Okay. So actually we can't directly derive it. Okay. So here we are not going to derive it. Okay, because it is not necessary at this time. Okay. So the derivation we are not going to do. Okay. Actually, if we have a sync function like this, sync square omega t type, okay, so Fourier transform of this function is a rectangular function. Okay, rectangular function. Okay, so here it is a, okay, a sync square omega t. Okay, so this kind of function we will have this kind of Fourier transform. A, so here it is from minus omega to plus omega. Okay, So this kind of function we will get. Okay, so this is in omega. Okay, this is in omega OF. Okay, so we have this kind of function. Okay, so we can't directly derive with. Okay, we have to derive the Fourier transform of this rectangular pulse first. Okay, so it can be done, no? Okay, it can be done. So you can find the function for this term and you can find the function for this term. Okay, and using the Fourier transform pair, you can evaluate this rectangular pulse Fourier transform. Okay, but it is not easy because we have to do very long integration. Okay, and I think we can use the differentiation property and find the Fourier transform easily. Okay, anyway, please try it to do if you have times. Okay, here we are not going to do it. Okay, so here we only use this knowledge. Okay, so please remember this. Okay, if you have a sinc function, a sinc is k omega t, you have a rectangular pulse like this. So I think we can write this as like this, no? A f by omega or 2 omega or something. Okay. So please check this. I can't remember this exactly. Okay, so please check this. Okay, my representation is correct or not. Okay, so anyway, it is a rectangular pulse. So the rectangular pulse will look like this. If this is omega, rectangular pulse has minus omega to plus omega, and the amplitude of the sinc square function is the amplitude of this maximum amplitude of this sinc square, rectangular pulse. Okay, so you can see that this rectangular pulse has this bandwidth. Okay, so we can assume this also as a narrow band. Okay, small bandwidth. Okay, so we can use the narrow band representation for the sinc square pulse. Okay, so we will this is the term we have gotten. Okay, so we can draw the spectrum like this. Okay, so we know that if you consider f, okay, so here 0, and here if we have fc, and here also we have minus fc. Okay, and you can see that this is a rectangular pulse. Okay, like this. Okay, this is minus omega to plus omega, and this is a. Okay, and you can see that here you have 5f minus fc. So that means the signal is shifted to this way, no? Shifted to this way. So here you have to find the shifted version. Okay, so that means if so you have, this is the 5f, this is the 5f you have. Okay, so here the 5 delta is also there. So here also 5 delta should be there, and here also 5 delta should be here. Okay, so this is 5 delta. Okay, so we have f. Okay, so fc, we have fc. Okay, and this is shifted to fc. So this point will shifted to fc. fc distance, and this also will shifted to fc distance, and this also will shift to fc distance. Okay, so you will have this kind of spectrum, no? Finally, so this point is fc minus omega c, omega is this is omega, no? So fc minus omega, and this point is fc plus omega. So this is the spectrum. Okay. So I think you can get it. So what we have done, okay, what we have done, I will summarize it again. Okay, we have the Fourier, we have the frequency spectrum. Okay, for modulated signal, narrowband phase modulated signal as AC delta F minus FC plus J by 2 AC 5 F minus FC. So to find this 5 F minus FC, we have to evaluate 5F. Okay, so we have to get the Fourier transform of 5T. What is 5T? That is 5 delta, our message signal. Okay, nominalized message signal, because here we have used 5 delta. So here the amplitude is already there. So we have to get the nominalized message signal, XMT. Okay, so we have to find the Fourier transform. Okay, so you can see that we have F, 5 delta F, our message signal, nominalized message signal. Okay, so we have to find the Fourier transform of nominalized message signal. So what is our nominalized message signal? That is sinc square omega t. Okay, so we have to find the Fourier transform of sinc square omega t. Okay, so we know that for sinc square omega t type function, Fourier transform is a rectangular pulse. So it is like this, rect t by 2 omega. Okay, please take this. I'm not sure these terms. So anyway, the function will look like this. The graph will look like this. Here it is A, this is 0, and this is minus omega, and this is plus omega. So we have found this. This is 5F. No, this is 5F. Okay, so 5 delta also should be there. 5 delta 5F. So 5 delta should be here. Okay, 5 delta A will be. Okay, so we have to find 5 F minus FC. So that means this is shifted to here by FC, no? So we have shifted. This is shifted here from 0. Okay, so we have like this, plus omega, minus omega. Okay, so when we do the spectrum, we know that at FC, we have that carrier terms. Okay, so our the information signal term will come as this. Okay, it is centered around this FC. No, this is FC minus omega, and this is FC plus omega. Okay, so that is how we can evaluate this. Okay, so I hope this is not much difficult question. Okay, so I hope you get it.